Thanks a lot. Okay, so welcome back to this session. So this is a joint collaboration with a number of people at Unity. We've been following for a few years, and also with Wang, who is a postdoc student now at École Polytechnique in Paris. It's entitled Real-Time Computational Cinematographic Editing for Broadcasting Volumetric-Captured Content. It's probably the longest title I've submitted, but anyway. So what's the overall context? Obviously, there is a clear interest, including financial, for main media industries to broadcast sport events. And this is done in a pretty traditional way, where a number of cameras are going to be placed around a football stadium or around any other sport events. And this is going to be broadcast in real time with an editing room where you have a guy and a number of assistants who are going to choose, okay, what's the best angle, when should I cut to another angle, etc., etc. So taking real-time decision editing strategies to convey the best content. So in the field, there's been a number of technical evolutions, and they've been using drones, for example, to improve what is happening over the scene. But there are also a number of other evolutions in the field that can largely impact the way the contents can be produced, captured, and consumed by spectators. So one of them is volumetric capture. So volumetric capture is the idea with multiple cameras you should be able to reconstruct a volumetric representation. So that includes both the mesh and the texture of actors, or here of people in sports, and in a real time. Well, not really real time, but today people are able to achieve a 1 second delay. So this is a volumetric reconstruction that was performed by Unity people with two sport players playing UFC, Ultimate Fighting Championship. So what's interesting with this is that it changes completely the way that people can consume the contents. It's not in a traditional way. They could probably move the camera themselves inside the environment, and they can choose angles which were not actually feasible in real life, because you can't put angles wherever you want inside this context. So there is a real interest in exploring how we can use this volumetric content for free viewpoint navigation. But when we talk with people from the industry, they want to create these novel viewpoints, but they don't want to really change the style. It's like when you're watching a football game, well, you want to maintain the style of the football shooting style. It's the same for other applicative contexts. So sports, they have these dedicated elements of styles which are related to how the cameras are placed, and these are due to constraints of the environment. It's also due to a number of artistic choices. They also have dedicated motion behaviors of the camera, how the cameras are going to move, how they're going to pan and to focus or to zoom on specific events. And of course, they have specific editing style. Editing is this art of cutting at the right timing between the different shots. So the question we want to address here in this work with colleagues from Unity is how can we encode this domain-specific knowledge in order to replicate the essence of this cinematographic style from a given sport, but also to enable more creativity by placing cameras at locations that can't be done in real life using volumetric contents. So there's been a number of contributions in the field related to that. First, in the broadcasting industry, so you've got multiple cameras that are creating some live contents, and there's obviously an interest in automating which is the camera you're going to select and how you're going to switch between the cameras. So what people have been doing is essentially working on feature extraction, so including audio feature extraction and estimation of game states. Different games have these rules, and in these rules, of course, the states are really important, and how the cameras are decided are clearly related to what's the state of the game. So once this analysis is done, well, then they propose different ways to automatically decide what's the best view, depending on the task, and how you're going to chain the different views together, because generally for one single action, well, you're going to use different snippets of videos put together. And this has been used, solved using really simple models. I mean, infinite state machines, Bayesian networks. So you just add some probabilities as to how long is the shot when you would cut. Hidden Markov models, which have the interest that you can perform some learning on data sets, or integer programming, because, well, it's a constraint solving problem. You want to decide which shot for how long do you want to see it. So that's for the broadcasting industry. We've got the pendant for the computational cinematography style, or virtual cinematography, where people have been looking at how can you automatically generate edits of a sequence using virtual cameras. So in this work, there's been a lot of rule-based editing. There's a lot of film conventions that can be easily encoded. So it's like cookbooks, recipes of how you would place, move, and cut between the angles. There was a graph-based approach with a PhD student of mine, Quentin Galvan, which is basically here you have the different takes horizontally, and then you would decide how much time you would spend in each take and when you would cut to another take. So it forms a graph, and then you can frame the editing problem as an optimization problem through the graph. There's also been a number of offline editing with multiple cameras and multiple takes of the same scene, and there's been a nice contribution by people in Stanford, Leak, who have been encoding rules using hidden Markov models, so also a Markovian process. So there's many ways in which you can formalize the knowledge and put it into computational models. So what we proposed here in our work is a fully automated framing, so deciding what the camera is going to look at, and a fully automated editing system switching between the cameras, which works for volumetric contents that is going to be guided by stylistic features from the movies, the sports shows, and that's going to adapt to user-designed view angles. So what's the steps? First one included watching a few hours of MMA fights or UFC fights. Not really my cup of tea here, but we had to go through that to get a better understanding of how things were done. And we run a number of statistic analysis on the contents to better understand what were the important features that the director was selecting or that the cameramen were selecting. So important features for the framing strategy, how you would frame different stages of the fight, and important features for the editing, when and how you're going to cut. And the second stage is, of course, once we gain this knowledge, how do we apply this knowledge? In the approach, we didn't use deep learning, we used a statistical approach here, but we're open to learning possibilities afterwards. Okay, so the general overview is that we have the real data, we have the live broadcasting, so we were working with the people from the UFC company, and we have the live footage from all the cameras and also the final edit. So we could gain some knowledge about why a shot was selected. So this was used as a statistical input to our system. And then we had this volumetric data, which was streamed live here, and we had different cameras that were placed in the environment. And what we did is, from the statistical analysis, we analyzed a number of visual features. So what's the orientation, relative orientation of the characters, what's the visibility, what's the inter-character distance, what's the face visibility, etc. And this gave us, for each camera, a score that is going to evolve over time. So how good, basically, is the camera in terms of features related to the UFC topic. And then with this viewpoint scores, we just had to decide, well, how long are we going to stay in a shot? And basically, when we cut, to which viewpoint are we going to cut if there are multiple possibilities? Okay, so statistical analysis. This is just a quick video to show how the cameras are placed in a real stage, even if this is a synthetic one. So they have 5 cameras. All of them are swivel cameras, so they have fixed point, but they can move horizontally. They can turn horizontally, vertically, and they can zoom. And what we wanted to do is to measure the correlation between the different visual features that we thought were important and the framing and editing decisions. So what we intuited from watching the videos and from discussions is that body and face visibility of course, of prime importance. The orientation of the body related to the camera, so whether the character is turned towards the shooting camera. What's the distance between the players? Because if they're far apart or very close, it changes the way you're going to focus on them. And also, what's the on-screen position? What's the composition of the shot? Where do you place the characters in the screen, or how do you move the camera to place the characters there? And also the type of shot. We'll see that there are 3 types of shots here in this UFC setup. Visual features. So we had the streams from all the cameras, and then we could run easily some 3D pose estimations using LCRnet. LCRnet is going to provide a 3D pose estimation, which is quite robust. What is interesting is, since we had the characters from different viewpoints, well, we could improve the pose estimation. And this simply provides us enough information to compute the body orientations, to have an estimation of the visibility of the characters, looking at the visibility of the joints, and to know where the characters were composed in the screen. So then we had these features we wanted to look at, and what we tried to measure here is the probabilities of how these features are going to influence the selection of a shot. So is this feature important to be shown at the screen? So we have this first probability, which is a probability given a frame I. So it's a probability that this frame from one of the camera is selected here. So is this frame selected when this feature is the maximum feature from all the cameras? Okay, so basically, is it the optimal camera that is selected by the director at this time? And we also looked at whether here, what's the probability that the frame is selected when the feature is not the best? So basically, how important is it to select only this feature, or could we have other competing features? So here the probabilities showed that, okay, all the features that we have identified are actually important in the selection process. And even if some of the features are not that important compared to other cameras, they can still be selected, which is shown by these low values. So then we displayed the histogram of feature selection over a window size. So, for example, this is the visibility score distributions. So, for one camera, what's the probability that we would select this visibility frame is selected? And we also displayed the distribution. So what's interesting here in this distribution, for example, in the visibility score, is fundamentally most of the shots that were selected displayed a very strong visibility of the characters. It's a bit less true for the orientation and for the distance. So overall, meaning of this is, okay, visibility is a key factor and more important than orientation and the distance, or facial visibility, which is in which there's often occlusions, and we see situations in which that happen. This is specifically related to grappling. When you have two characters, two players, one above the other, it's very difficult to understand what is the important criteria. Okay, we also looked at the different types of shots, and we recorded the distribution of joints on the screen. So there are three types of shots. So the cowboy shot. So cowboy, you would see the shoulders of the characters, and you would see a bit of the feet of the characters, or you would cut at the knee level. The full shot, where you would see the whole character, and the large shot, which is a more far away taken shot. And this showed the distributions, and these distributions are important because it shows how the filmmaker or how the cameraman is moving its camera to maintain these compositions. And we also measured from the data set transition probabilities, so very easy. We have the different types of cameras, 1, 2, 3, 4, and 5. And basically, we just measured what's the probability that we would cut from camera 2 to camera 1, from camera 4 to camera 1, etc., etc. And this is very easy to measure. So once we have that, oops, sorry, I'll go back here. So once we have that, we derived some statistical values, and the idea was to input these statistical values in an engine that would be receiving the flow of information of the visual volumetric content, and here identifying whether these features are there and how we could use these features to make the decisions on framing and editing. So to do that, we had not only the volumetric representations. We made 4 renderings of different characters on this volumetric representation, and we applied LCRnet on each to be able to identify what were the poses of the characters and to extract the features. Because what's important to understand is with the volumetric data, well, you just have a polygon soup and you don't know what's the hand, what the head of the characters, etc., etc. So that helped us to provide the distance and to character distance, character orientation, head orientation, and screen positions just by using, and this is the LCRnet computation. And to compute the visibility, well, we used some geometry proxies on the characters. So here there's a lot of noise in the pose estimation, which is classical, and it's related to LCRnet. We could have smoothed it out, but actually we decided to perform the smoothing at a much later stage, at the stage where we're computing the score. It showed to be better. Okay, in terms of framing, so that's the input. We have the volumetric content. We extract the features from the volumetric content, and now we need to take the decisions. So in terms of framing, depending on the type of camera, we fundamentally worked with the people from Unity. They designed the Cinemachine engine, which is an engine inside Unity, which does the cinematography, and they transposed this distribution here of characters into a framing strategy. And this framing strategy included trying to maintain the characters separate on left and right here, and also zoom as soon as the characters are too close. Zoom in, you would too close, and if they're too far, you would zoom out. Okay, and then what we could compute for each camera. So we had this automated framing system, which was deciding what's the best angle, and then we need to decide what's the score of each camera to be able to perform the cuts between the viewpoints. So we had a very basic here utilization of the different features we extracted. So typically D is the distance between the characters, W is the visibility. I don't know who's pinging me. Sorry for that. This is the visibility, and basically we're going to use the visibility a lot in the equation because we saw it was an important criteria. We performed them, so this enables us to compute the score of each frame I and for each camera C, and we performed some smoothing because there was some noise, but we performed the smoothing at a later stage. So For all cameras, we have a live score which is running, and then we need to decide how and when to cut. So decision to cut was based on an improvement factor. So basically, if there were another shot that was 10% better in terms of score, then we would go and select the other shot. And if there were competing shots that were 10% better or more, we would use the shot transition probabilities to perform the cut. So it's heuristic, but it's simple and it's super efficient because it needed to run in real time. Okay, so here's a display of the tool we worked on with Unity. So here the hemispheric representation is giving an idea of the score. So blue means it's a good view angle. So we performed the sampling just for the display. We performed the sampling of all the viewpoints around. Blue means there are good viewpoints, and red means the viewpoints are not so good, so the scores are quite low. And then here we've got different cameras which are placed here, and we can compute for each camera the score, and you see the score evolving over time, and the system automatically selecting here the optimal camera at this time. I'll just move a bit through the video. Okay, so here's the 5 standard cameras that are set up, and we were using exactly the same setup. We'll see afterwards how we changed to other camera systems. So we've got the volumetric content. From the volumetric content, we extract the pose, we compute the visibility, we extract the other features, we then compute the score and decide on the editing process. Okay, the fight is a bit long. So you'll see here we get to this grappling stage, and the grappling stage is a bit difficult. You'll see the pose estimation of the characters for SIGGRAPH is, of course, creating a number of issues. It's very difficult to estimate because it's not able to link the individual joints of the characters that are detected together. Okay, and this is the final result shown. So when we were typically in grappling phases, we changed the strategy, and we were not looking at body poses and body orientations, but just at faces of the characters, and we wanted to improve the shots where we could see the faces. So it's very empirical in that way. Okay. Sorry. Come on. Okay, so we generated some results, and the key question we had is how good are these results compared to the real content. What we proposed here is to use a specific metric. Our idea was to say that, well, if you have a sequence of cameras, it can be considered actually as a sequence of string characters. Each type of camera can be a character, and there's a number of metrics that have been provided by the community to measure distances between strings and editing distances, so how much a string is similar to another in this context. So we use the TWED, which is time warp edit distance. And what's nice with this feature is that it accounts for a number of temporal for certain temporal elasticity, between the different edits. So even if the timing of the cuts were not perfect, but we had the same type of shots, it provided a good metric. So we run these computations using TWED. We had the baseline strategies, which is a very simple editing systems, and we had different variations using only visibility, character orientations, or on-screen distance to compare the results. Here we can go into the details if you want after. We also run user evaluations. We displayed in a pairwise comparison the different results, and it showed that fundamentally our approach was performing in a way a bit lower, but similarly to some contents generated by the experts. It was way better than random case and way better than a default strategy we had implemented. Then we also played with the system to show how it could behave with cameras that were designed by the users or even placed randomly. So in this situation, we placed a number of random cameras. So there's 20 cameras that have been placed in the system and just rerun completely the whole sequence. So we had just a distribution of these cameras on the hemisphere in terms of position and distance to the characters, and the results, in terms of edits and in terms of framing, appeared super reasonable to the collaborators from Unity and also to the people from the UFC. Okay. We also asked some artists to position manually, a number of cameras that would appear relevant in a fighting contest. So here the cameras were placed, and in the same way we measured the different aspects related to the different features, the score of the system, and we came out with some interesting results. What's good here is that it provides some view angles that were not able to provide in a real context, because here you've got some very low angles that are interesting to show some specific parts of the content. So basically it showed that it scaled quite well to non-standard locations, and that was beneficial to the UFC audience. I think I'm running short on time. Okay, so conclusion, it's obviously, and you see it, it's quite an empirical approach. So we extracted the features and we looked at the best way to compute the qualitative value of the shots. But what we believe, it's an interesting framework that can be reused, because we provided also a number of metrics, and including validation metrics using a TWED. For editing strategies. Now, how are we thinking to improve the work? While exploring aspects related to nerve and 3D Gaussian reconstructions, obviously we can have a better content quality, which is of strong interest for the people from USC. And also we can make a number of edits on these contents, so typically change aspects related to lighting, which is of interest. And now the next stage, is trying to think of really more cinematographic paths. So you could imagine in a fight, there is this fist which is arriving in someone's face. And then, you could run a slow motion of this using a style that is inspired by a real movie. So currently what we're doing is extracting a number of features from movies. And unfortunately, that requires me to watch a lot of Ultimate Fighting MMA movies, which is, again, not my cup of tea. But we're extracting camera trajectories from these setups and trying to learn strategies from them, and to be able to automatically generate cinematic trajectories with these volumetric contents. And that ends my presentation.
Thank you.